Hello, I'm Zhou Zhao from Rice University. So here I will present our collaborative work with Jacob Arzon, Gonja Verma, and Santiago Segarra on congestion-aware distributed task offloading. By the end of this talk, you will learn how we could leverage graph neural networks to mitigate congestion in various multihop networks for computational offloading. So this presentation has been given at the ICASSP 2024 in Korea. Here it is reproduced for YouTube. The context of this work is in wireless multihop networks. So there are three types of nodes. The first are the clients, which generate data but is resource constrained. For example, drones with cameras. We also have servers that has rich computing resource and a dedicated relay that can relay information from one to another, but has no data nor computing functionality. So here every node can relay information from one another, but these relay nodes are the dedicated relay. So we consider tasks that can be modeled as a steady flow of similar jobs. The best example are object detection in a video frame and in a video stream. Here each job would be object detection in a single video frame, right? And then different jobs are independent from each other, and they all have the same data size and do the same processing. So the clients will make decision on where the computation should happen and through which route it will upload data to the server. Moreover, multiple clients will make parallel decisions in a single batch, and after the decision, streaming will start. The objective of these parallel decisions are to minimize the average job response time. So the baseline approach to this problem has two steps. In step one, each client will send out packets, probing packets throughout the network to learn the topology of the network and the capacity of each link and each server. With this information, each client will build an edge-weighted graph that like this. So here the edge weights represent the unit cost of sending flow through that link. For example, this could be the inverse of the link capacity. And for the servers, we will have a virtual link that connects the server to a virtual sink, and the edge weights is the inverse of the server capacity. So then the offloading and the routing decision can be made by finding the shortest path between clients and the virtual sink. It looks like this. So what could go wrong with this baseline approach in the context of wireless networks? We often find that once the streaming started, the link capacity drops. Moreover, the amount of link capacity reduction also depends on the decisions of those clients. So the reason of this phenomenon is that the wireless network can be modeled as a queuing network with interference constraint. So here each wireless link is modeled as a queuing system where the queues are buffers hosted on two ends of the link, and the link itself is modeled as a processor in the queuing model. And when a packet is processed by the processor, it is transmitted from one end of the link to the other end. What happened during probing is that a packet can travel through one link at time t, and then immediately through the next hop at t+1, because the network is essentially free of traffic. But this is very different during streaming, where all the queues are filled with packets, but a node can only talk to one of its neighbors at the same time. So when transmission happens between 3 and 5, these two links has to be stopped and the packets are waiting in the queues. Essentially, this means that the link capacity is shared among conflicting links that has traffics to send, and those traffics depends on the decision of those clients. Obviously, in our decision model, the problem comes from that the clients are making parallel decisions without knowing each other's decisions. How could we address this shortcoming of this distributed greedy decision? One way is to involve centralized scheduler that collect all the information of the network and make sequential decisions. but this solution will involve high communication overhead to collect the information from the whole network. And moreover, if the scheduler fails, the whole network will black out. The other way is to incur some pure coordination between those clients, right? So decide a random arbitrary decision order among those clients. But this approach is difficult for large networks, and it also incur high communication overhead. So our solution is to keep the shortest path decision framework, but change the edge weights. Particularly, we propose to encode the network context into congestion-aware edge weights. For example, these numbers here. Right? So these edge weights can help to improve the outcome of the distributed grid decision, right, without changing the decision framework. So here, the first question will be what is network context? It includes the network topology, the average link rates, and the interference relationship between those wireless links. It also includes demand and supplies, such as which client has tasks to offload and the required flow rate of each task. For the servers, this will include which nodes are servers and their capacities. In particular, the interference relationship can be modeled as a conflict graph. Here, each node in the conflict graph represents a wireless link, and two nodes in the conflict graph are connected to each other if their wireless links are conflict with each other. In other words, these two links cannot be turned on at the same time. Now let's look at our pipeline. The first step is to build this graph model. So we introduce a virtual node and virtual link to every computing node that include all the clients and the servers. The rate of the virtual link represents the computing bandwidth of the computing node. Then we assign the demands or the initial flow rate to the virtual link associated to clients that has tasks to offload. Right. For the rest of the links, the demands are 0. For the convenience of processing using graph neural networks, we also build these conflict graph and extended line graph. So here, essentially, for the extended line graph, it will convert every edge in the extended graph into a node, so that edge features now converted to node features. And two nodes are connected to each other in the extended line graph if their corresponding wireless, if there's corresponding link share the same node. But conceptually, we can still refer to the extended graph. Now, once we have the graph model, the first step is to predict the edge weights using graph neural networks. So here it includes 2 steps. First, we use the graph convolutional neural networks. This is a trainable block to predict the traffic load on every link. So these are the axes. Then we feed the axis and the link rate as well as the config graph into the CSMA digital twin, which will predict the edge weights or the link unit delay. Those are the deltas. So to dive in a little bit in the CSMA digital twin, it is a differentiable graph process that predicts link unit delay under the CSMA scheduling. So CSMA represents carrier sensing multiple access, which is one of the most popular media access control mechanism for random access network. Essentially, it will give contending neighbors this equal chances of channel access. So we use this principle and a queuing model to build this CSMA digital twin, which essentially iteratively update the long-term link service rate and the contention probability of each link. Or in other words, how likely a link has traffic to send. So once the link service rate converges, then we use this equation to compute the unit delay on every physical links. So these equations coming from the queuing model. So once we have those edge weights, deltas, the offloading and routing decisions are pretty straightforward. we just find the shortest path between the clients and the virtual sink. Now let's look at how we train our GCN. Right? So here we convert the task execution block into a CSM ideal twin followed by a cost estimation block. Right? So with this training pipeline, we just draw random test instances, feed into the pipeline, and get the cost of all the flows. The GCN here is the only trainable part in this pipeline. Then we use backpropagation and stochastic gradient descent to train the GCN by minimizing the sum of two objective functions. The first objective is the total cost of all the flows, or total delay of all the flows. And the second objective is the mean squared error between the forecasted and the empirical link unit delay. This serves as a regularization. So here we introduce a trick to bridge the non-differentiability gap introduced by the shortest path algorithm. Essentially, we assign a negative gradient on each link on the shortest path as the gradient of the forecasted link unit delay. Right? The intuition behind this is that by increasing the weight of the link, we can reduce its chance of being included in the shortest path routing decision. Now let's look at our numerical results. We generate random test instances by first creating random network topology using Brabazzi output model. It looks like this. And then we create offloading instances by assigning different roles to different nodes. The central nodes will be relay, dedicated relay, and for the rest of the nodes, 80% will be clients, 20% will be servers. And 80% of those clients will have tasks to offload. So we create test instances from network of 20 nodes to network of 110 nodes. And then for each network size, we create 100 different random graphs. And then for each graph, we create 10 random offloading instances. And when tested offloading policies of these three different policies, the total simulation time is 1,000 time slots. Here we show the task congestion for this test. The blue lines, the solid blue lines shows the task congestion ratio under the baseline approach, and the green are the GM-based approach, and the orange are the local policy. So local policy represents that all the clients just run their own task without offloading. So we can see that the baseline will introduce 4 to 15% of the chance of congestion. So here congestion means that the execution latency is greater than the simulation horizon. But the rest, the local and the GM policy doesn't introduce any congestion. The execution latency of the baseline due to the congestion ranges from 100 to 500 time slots. But for local and GM-based policy, they are equal or less than 20 time slots on average. So here we can see that the GM-based policy achieved the lowest average execution latency. Now let's look at the individual behaviors of those tasks. So the question here is, what happens if a task is not congested under the baseline policy? So what we show here essentially is that the baseline policy will yield the lowest average execution latency if a task is not congested. So it shows that the baseline policy is a very aggressive policy, right? Either congested or achieve the lowest latency. But still, the GN is better than the local policy, and but it's worse than the baseline. If we further look at the average hop distance between servers and clients, we can see that the GM-based policy favors nearby servers compared to the baseline. And also this result shows that the performance of the GM-based policy is still too conservative, and it has room to be further improved. So to conclude, in this work, we we formulate distributed task offloading and routing as the shortest path routing problem, and then we encode network context into edge weights to mitigate congestion of these concurrent flows of jobs. So this work can be further improved in 4 aspects: from the decision framework, the training approach of the GCN, and also the digital twin, as well as the simulation platform. Thank you for your interest. Please check out the paper and code.